So welcome to today's session. We'll be discussing state space models. This will be done over the next two sessions, today and tomorrow. 3 hours today, 3 hours tomorrow. I'll be taking the first 1 hour. I'm Veda from 1024. We'll start off with a feature that I'm sure everyone knows is autocomplete, where if you put in a bunch of words in your keyboard, you can see it suggests a few words, and this is just basically. So what we're trying to figure out here is how you see here how it works. So you want to understand how autocomplete works. This is what you want to build. You want to build a model that takes in a bunch of text, that's our input, and as output it gives this. But before we go into the model part, we need to understand how do computers even look at stuff like this. Because all the computers only work in terms of numbers, they don't really understand text or images or anything like that. So how do we make them understand things? For this we use vectors. Vectors is basically a numerical representation of human known concepts. So for example, if you have a house, let's say the house has 3 bedrooms, it's 2600 square feet and it's 10 years old. Now if I tell this to a human, then they'll understand what I'm saying, but a computer doesn't really understand all these words. So we need some numerical way of representing this to the computer, and how we do this is by vectors. So a vector is simply just a list of numbers that the computer can understand. But it's an ordered list. So order basically means that you cannot swap 2603, because in this it is implied that this is bedrooms and this is area. So if you swap these two, then obviously 3 square feet doesn't really make sense. So for something like this, it's pretty obvious how we get the vector. But how do we do it for something like maybe an image or text or words? For an image, what we do is it usually has a bunch of pixels. Let's say you have a 20 by 20 image. That's 400 pixels. So what you do is you store 400 values in one vector and you pass it into your model. That becomes your input. For words, what we do is, let's say you have a vocabulary that is just 5 words. Now we want to find some vector representation for each word. What we can do here is we take a vector that has the same length as vocabulary, which will be 5. And we assign a position in that vector to each word. So let's say cat is the first word, dog is the second, pizza is third, and so on. Now, if we want to indicate that any word is present in that, we'll simply put a 1 in that position and zeros everywhere else. So if you have cat, that will be 1 and then 4 zeros. If you have dog, that will be 0, 1 and then 3 zeros. So this is what you get. This is one way of converting this word to a vector. Now, this is a vector that has only a single one and zeros everywhere. So we call this technically a one-hot vector. Similarly, you can just expand this to the entire vocabulary, where you take all the words rather than just cat, dog, and these. And so you get a much longer vector, but it will still have only one and all zeros. So every dimension in this simply, so this is a dimension, this is one dimension, this is the second one. A dimension in this vector simply represents whether or not that word is present. So here it says cat is there, here it says cat is not. That's how we do it. But this is pretty simple and also intuitive, but it's not that practical, because the length of the vector will have to be the same as the length of your vocabulary. So if you have a lot of words, then it doesn't really make sense to have such a long vector. So how do we improve this? We use dense vectors. So sparse, there's 2 kinds of vectors, there's sparse and dense. Sparse is when most of the elements are zeros and there are few non-zero elements. Dense is when all the elements are usually non-zero. So we want to get some sort of dense representation for this, and we also wanted to encode some sort of meaning. If you see here, this doesn't really encode any meaning. This is just saying whether or not that word is present. But we know language, the words usually are similar or dissimilar, things like that. For example, cat and dog are more similar than cat and pizza. So we want our vectors to also have some sort of meaning. They should encode some semantic information. For that, we use dense vectors. We'll not get into how they come up with these dense vectors. That's not important for this session. But this is just to know that something like this exists. So, for example, if you usually have a dense vector has a lot of dimensions, but not as much as the one-hot vectors. And let's say you have a vector for king and a vector for man. What you do here is, if you take a vector king minus man, you get this thing. And when you apply this vector to woman, we notice that you get queen. So what that means is this representation is encoding some sort of meaning, because the same vector takes us from man to king and from woman to queen. So write that as impression. We get this. So dense word vectors capture the meaning. One-hot vectors don't, but one-hot vectors are usually simpler to understand. So that's what we'll use for the rest of this session. And so we're done with the input and output, how we get how we format this. Now we look at the model. Now to make the model, we take the most popular one first, neural networks. I'm sure everyone has heard it. How about we just try to apply this onto the output we have. Before I get into like how we apply it, I'll just give a quick intro of what a neural network is. This is a neuron. This is a biological neuron. The computation neuron is different. It's a basic computation unit of a neural network. It's what takes in the inputs. It does a bunch of calculations and manipulations to that and gives you an output. This is a neural network. Neural network is made up of a lot of neurons. There's the first layer that's called input. Last layer is called the output layer. And then you have a bunch of middle layers. Now, when you decide that you're going to use a neural network, you have to fix this architecture from before. Architecture basically means how many, what's going to be your input dimension, what's going to be your input layer dimension, like how many neurons are you going to have here, how many here, and then what's going to be your output. This is fixed before we start the training. That's an important point because we'll see it later. This is an example, just one neuron. If it has, let's say, these three weights and these three inputs, we're basically looking at the first, like this one, just a little more in detail. What this neuron does is first, it takes a weighted sum of the input vectors and it adds a bias term. Then to this weighted sum, we apply an activation. Activation, we have functions like sigmoid, value, and things like that. But this is what one neuron does. This edge is finally the output of this one neuron. Now here, this is for all four neurons. Again, Z1 will be a weighted sum of this, Z2 will be a weighted sum of this, but they will be different weights. And instead of writing the equation for every single neuron, it's going to be easier to represent it as a matrix. If you evaluate this, what you see is you get Z1 is equal to this dot this plus B1. And then Z2 will be this dot this plus B2. So we're basically writing what we wrote in the previous slide, but in the more shorter compact way using matrices. We can also write this each one as W1x plus B1 equals Z1, where W1 is the weights associated with the first layer. And B1 is the bias associated with that layer. Again, once we get this Z is just the weighted sum, it's not the output of that layer. So we apply an activation to this, and the output of this layer is your H1. That's how this works. H1 is simply, you take the weight, multiply it with the input, you add a bias term, and then you apply your activation to that. In this case, you take the hidden layer, but the same logic works when you go from one hidden to another hidden rather than just one input to one hidden. So if this is your network, then H1 would be W1x plus B1, and you apply your activation to that. H2 would be W2 times H1. So if this is your input, this becomes the layers weights which you consider. You add the bias term, you apply your activation. Similarly, this is your prediction. What prediction is denoted by that? So you take weight, you multiply that, you add bias, and that's your activation.
Anyone has any questions so far?
Did I go too fast? So it's an activation function. Basically, the point of this function is to make it non-linear. Because if there's no activation, then it's like imagine you have a bunch of data points, you're basically only trying to fit a line. But it can be like it's non-linear, you want to fit curves and all. So the main point of the activation function is to introduce some non-linearity. You usually have functions like Z or so like you have a function that, let's say, this is your weighted sum. What it does is it returns this code. So this is your F of Z. So it makes it non-linear, but helps us capture more complex patterns because real-world data is actually more messy. So that's why we need to apply this activation. Any other questions?
What is Epoch like when it's applied to a maintenance? It's pretty obvious where it is like when you apply to a single thing.
You just here you just apply to each element. You don't.
Can you switch the pocket of the receiver? Put it away from the board. Other pocket.
So now we know, like, this is the math. Try to get used to this matrix notation. We see it a lot. Basically, the output from this third layer is W3 times the input to that layer plus a bias term. And then we apply an activation to that. Activation is to reduce some non-linearity so that we can capture more complex patterns in the data. So now we have a neural network. The input will be the given text. The output can't be the word vector exactly. We said that encoding the word as a vector, but the output cannot be a vector because, as I said, when you have a dense vector, which is what we use practically, for a particular dimension, let's say you have very long and second empty. Let's say the actual word has 2.1, but then there will be another word which has, say, 2. Everything else will be different, but these two are pretty close. Now your model will never be able to accurately give just the correct words vector. It will give you some approximation if you make the goal that we should output the word vector. So what we do instead is, like, let's say I give you a sentence, MS Dhoni plays dash. Now what you'll do is you'll have some guess in your head that this next word could be what. If you see plays, even if you don't know who Dhoni is, you'll say okay, it's probably some sport or some game. So you give some sort of probability in your mind to each word. So you, like, MS Dhoni plays, you know, okay, pizza is going to be 0 because that's not a sport or a game. But he plays golf, for example, he plays cricket. The highest probability you give to cricket, but you can't say golf is 0 because he does play golf also. So what we do is, we ask the neural network to do a probability distribution over the vocabulary. Basically, for every word, the network should say, give a probability from 0 to 1. Say how confident it is that it could be that word. So let's say if you have your 3 words, MS Dhoni plays pizza, cricket, and golf. If you give pizza 0 probability, ideally. If you give golf, let's say 10%, and cricket would be 90%. Once you get this distribution, we can take the most likely word and we can use that as a guess for the next word. So we have the given text and we have the input. But so far we've only seen how to encode a word. For a particular word, we can map that to a vector. But how do we encode a sentence? Because a sentence is a bunch of words, right? So how do we take that and make it a vector? The first way, and the most seemingly logical way, is we just stack all the vectors. Like, let's say the sentence is I live in France, I speak dash. Now each word in the sentence will have its own vector. We can assume that to be about one hot, the logic remains the same. And we stack them. Stack basically means you put it one on top of the other. And now we pass this as input to the neural networks. Now there is one very sort of glaring issue with this method, is that remember I said that neural network only takes a fixed dimension input. But obviously the number of words in your sentence can vary. It could be, in this case, it's 6, but it could be 4, it could be 3. So the number of vectors that you stack, that keeps changing. But the neural network has a fixed input dimension. So we have to somehow encode this sentence, but into a fixed length vector. How do we do that? We can't do it like this because the number of words keeps changing. So then the next intuitive way is, okay, I'll just fix how many words I'll see. Like, let's say I want to predict the word here. I'll just look at the last 2 words. That's one way, because then you're fixing the input dimension. It will always be whatever the word vector is for one plus that one for the next one. So it will be 2 times dimension for your word vector. Here there is another issue. The input issue is fixed and the dimension has been fixed. But now if you see, if I pass just this into the neural network, I speak, it will give me a probability over the next few words. Now the fact that you're saying I speak, you can guess that it will be some language, like it will be English, French, whatever. But it cannot see France in this case. It only sees I speak. So it doesn't have any way of looking at the context, looking at what we provided so far, and then giving a proper guess. So in this case, the model might just guess English because statistically that's the most spoken language. But the actual answer in this case should be French. So the issue with this method, if you fix the context window, is that there is no memory. The model loses information from the sentence. You could say, okay, maybe just take n equal to 3. But then that's only for this one particular sentence. You don't know where the core information is stored in like a whole variety of sentences. So we can't fit a context window and then stack with this. Does not work. There's a third way for this, where if you have some sentence, you take the word vectors of each word and you just add them up. So if you see this, let's say this is for the cat, weight, the mouse. These are what not vectors. If you just add all of them, you get this. Now this vector, you could think of it like, okay, this first point, this is for the. So this means that the word the is present. This shows that this is for cat. This shows that the word the is present. This shows that the word cat is present. So if you look at this vector, technically you should say that we have the cat, weight, the mouse. But the issue here is.
If you don't have the issue, then guess.
What's the issue? Like the model can only see this part. It can't see all this. So what's the problem with this? Yeah, exactly. It doesn't know the order, and language obviously order matters. Maybe this becomes the mouse ate the cat, or just a part of the time to bunch of words.
And tenure suggests a method to fix the ordering. What would you do?
Instead of having it be all one, you have the first one, you put like the distance is to the word you import into the value that is related.
Right. And do you have any suggestion on how you want to encode this notion of distance? Add a few extra bits. Okay, wait. Wait, what do you say? By some weight. So you are saying this will be 0.2, this will be 0.4, 0.6, so on. The downside with that is it's going to like also then your words are going to get more weight, right? So then that will affect. But that's a reasonable idea. You also have some idea.
That's what I was saying. Like you enumerate, so the first one.
If the network sees bigger numbers, it might get more important to calculate. So you don't want.
Okay.
If you give the last numbers more weight, then people again either context is very sure.
Or you can use complex weights.
Yes. Now that is an interesting idea.
Yeah. The same issue is with dense also, but it's easier to like visualize. The logic is the same.
But the second, so there's two things. The second thing, neural networks usually is you initialize all your weights and you let the model train, right? So you need to also make it easy for the network to train. So if you put in biases of this sort, it might make it harder to converge to a solution that attends to every word properly. But Alta's solution was interesting. Instead of dealing with weights as a particular number that keeps increasing, you set it as a complex number. Then this is a rotation, right? So the first one is a 0 degree, second one is a 10 degree. Everyone knows E raised per I omega, and you can change omega, right? I will not tell you, we will not get into how this is used, and this is like one possible option we can go into. But maybe like somewhere later down in the session I can interject once again and see if we can make use of that idea. Yeah.
So there's three issues in neural networks. First, they have a fixed input length, but every sentence has a different number of words, so that keeps changing. If you want to fix the context and say that we only take the last few words, then there's a memory issue. It doesn't have any information from the previous words. And the last one, they might mess up the order. That is, if you take this one into consideration. So, just to summarize what we've done so far, we wanted to see how we model autocomplete practically. We started off with how the computers understand words and just things in general. We looked at vectors for any general, we took the house example. Then you look at one-hot vectors, basically 1 if that word is present, 0 if it's not. Then we looked at, okay, we try neural networks to model this. We looked at neural network, the neuron, the way it makes it, everything like all that. Then we tried modeling autocomplete. But then we got issues with that. The first is fixed length, second is no memory. So neural networks are a flaw for this method. We have to come up with something new, something different. And This is what we want. We want a model that can handle intelligence, maintain internal memory, and consider order. Because that's the thing about language, order is important matters. So the most, like, when we don't know something in AI, what scientists tend to do is our best source of inspiration is human beings. If we can do it, then we gotta look at how we did it, and then we try to model that in a more computational way. So how do we understand text? If I give you this sentence, I live in France, I speak. It's not that hard to guess that the next word will be French. But let's see what your mind did in like a split second. What you did when you read the sentence that helped you guess the word French. So first, you read a sentence one word at a time. So that gives you a hint of how many words you should consider. Because human beings only consider one word at a time. And as you read the word, when you read I live in, by the time you reach France, you have an idea that this word is going to tell you something about the location of where you are. That's because what you read in this part, you carry that information forward to this step also. You didn't just read this and then discard it. You read I live in, and then you're going to be like, okay, now it's going to tell me, okay, my location. It says France. And now when you see speak, you know that the next word is going to be a language. But to see which language it is, you refer to France. So because you remember what you read, you can guess from France and a language that is spoken in France. You can guess French. This is the very important part. This is the core of this, my part of the session. Is that every time you read a sentence, first you look at it one word at a time. Second, once you finish a word, you don't just discard the information from that word, you remember something from it. You might not remember all words equally, and you look into that later. But you remember whatever you read, and then you use that information to guess your next word. So if I just show this in a bit of a, sort of way. We read one word at a time, we maintain an internal memory as we read each word, and the memory influences how we process the next word. If I show this in a little fancy way, when you take in the word France, if you just read this word, you see, okay, France is a country. What is it about this country? You have no idea. But because you read the previous words and you read I live in, you could understand that this is your location. You updated this memory to something like, okay, location equal to France. And now you can use this memory to maybe either guess, predict the next word, or you can use this memory as memory for the next word. Like when you take an I, you remember France also. So again, reading a word, you are also using information that you got from the previous words. You update that memory. Now you can use this memory either to predict the next word, or you can use this as memory for the next word and keep going. In case of France, we're not predicting any word because we have no more words after this. But when you read speak, after speak there's no other word. So you have to make a prediction. So if I just put a box around this, what you're doing here is you process the current word, you process the memory until the words you've seen before this word. You update your memory. Now that updated memory, you can either propagate that to the next step, or you can use it to predict a new word. So this is what we do. And now we can just make some sort of computational way of this, and you can train a model like that. So I'll make this box a circle. This circle takes in two inputs. It takes in the word France as one input. It also takes in the memory from whatever you've read so far, that's I live in. So that comes here. Now it processes the word, it updates your memory. And now based on this memory, you can either make a prediction or you can use it as memory for the next step. This is the main key thing. This is that you're taking your memory and you're also sending that to the next step. That's how you can build this. So once you've read this, we pass it into another processing unit which takes in this memory and the word I. Now you can again make a prediction, but we're not going to do that because we know the next word. You can pass it to the next one and it takes speak. Now once you read speak, there is no word after this, so you have to make a guess, and that's when you guess French. Even though you don't live in France, obviously, you can still guess France, French, because you remember what you read. So this is the model that captures whatever we humans do. Reading one word at a time, making memory, and using it. This memory in ML, we call it the hidden state. Again, we have a lot of fancy words in AI. Hidden state is one of them. The hidden state stores the information from all the previous steps in a sequence, and it is updated at every time step. Time step basically in the case of a sentence, a time step is every word that you read. So after every word that you read, you are updating your memory, the hidden state. And the hidden state at any time step T, that is the hidden state after reading a particular word, depends on that word and the hidden state from the previous time. So we're basically saying whatever we know after reading the current word depends on the current word and whatever we learned from the previous words. This hidden state is the most, like, it's the core part of this architecture. That's what makes it very unique, and it's also used a lot in state-space models. So keep that in mind. If you look at this now in a little math there, we have an input, say xt. Xt is basically input at time step t. Again, time step doesn't mean time in the literal sense. In case of a sentence, it just means a word. We send that in as input to our system, but it doesn't take just that particular word. It also takes your memory from the hidden state from the previous words. That's passed as input. It processes these two to give you the hidden state at the next time step. How we get this is, again, as we showed in the neural network slide, we use weight matrices. So this is a vector of this particular word. This will be a vector of the hidden state. How we get the new hidden state is you multiply this vector, this matrix with this, you multiply this matrix with this, and you again add a bias term, and then you apply your state activation to that, and that's your updated hidden state. Again, as we said, hidden state is a function of the current entry and the previous hidden state. Now, based on this new hidden state, you can make prediction, or you can. How you make the this prediction, which we call y hat t, is, again, we have another matrix for that. Now, can you guess what we'll apply this matrix on? Like, how do we'll multiply it with one of these vectors, but which one of these vectors will we do? Like, what are we using to make a guess? So then which one will that be? Like, we've read this. Yeah, we'll use this because this basically means whatever we know from everything we've read so far. So that's what we'll use when we make the prediction. Again, it's the same thing, multiply the matrix with the vector, add bias, and then apply an activation. So this is called the recurrent neural network. It's recurrent because we're applying the same thing over and over to every single time. So t is any number, so it will be x1, which is the first word. We then apply this same thing to the second word. That's a very important part of this type of network, is we're applying the same weights to every single word. We're not changing how we process each word, because even when you read a sentence, you don't do anything different for every word. We're applying the same answer there also. So, if you look at one forward pass of this, forward pass basically means you pass in the inputs and you see what output you get. Let's say I give you 3 words, okay, and let's say x1 is the input. I pass that to the network. On the network, we have a weight associated with the input, but we don't consider only the input. We also take the starting, like it's 0, which is weight state at time step 1. Basically, we could initialize that to 0 because technically you don't really know anything until you write it. So weight 0. Pass that in. We have a matrix for that also, and we calculate h1. How do we get h1? Again, multiply this with this, multiply this with this, add a bias term, and then activate it. So that is h1. Now, again, using this updated memory, we can either predict the next word, or we can pass that as memory for the next word. Because I've given you 3 words, and I want you to predict the 4th. I'm not going to predict anything yet. We just pass this on to the next word. Now we take the next word, which is x2. We again have the same matrix associated with this. Note that these two are the same. So we only have to learn this one set, and then we apply that to every single word. Pass that in as input. We calculate h2 in the same way. Again, we don't want to make a prediction just yet. We have to read the last word also. Pass that as input. Same matrices, and then you get h3. Now that you have h3, there's no more words left. You have to make a guess. You make a guess using your latest memory, which is h3. How you do that is you have another matrix. Okay, this notation basically means we're going from x to hidden state. HH means you're going from hidden state to hidden state. HY means you're going from hidden state to output. That's how I'll name the axis. So you make your output. That's one forward pass of the neural network, and that's how, let's say, given 3 words, you can guess the 4th word. Also, one thing to note, this y hat 3 is not a guess for x3. It's not guessing this word, it's guessing what the next word would be. That's a confusion I had seen first. Okay, so now how do we take? Let's say we have 4 inputs, we have the output. We usually, once we do a forward pass, we have a loss function that compares how good or bad our guess was compared to the ideal value. So let's say we have a loss function that compares, this is ideal case, this is our guess. Now we use backpropagation here. Backpropagation, if you're not familiar, it's basically we use chain rule to see how each weight matrix affected this loss. How we do that is, let's say we want to find the derivative of this loss with respect to h1. Now we can't directly do it because there's a lot of intermediate steps involved. What we do here, we know del L by h4 because this is direct a function of h4. Now we know h3 by h4 by h3. We know h3 by h2 and we know h2 by h1. So if you have to find del L by del h1, you can simply do this. This is using chain rule. You must start using chain. So that's what we apply, and that's how we train the network. So just a more general form is loss with respect to a particular weight state is loss with respect to the final one, and then all the internal ones. So you get h4 by h3, h2 by h1, h3 by h2, h2 by h1. I'll just stop there. Does anyone have any doubts here? This is part 9. Okay, so basically we have weights, right? That's what decides our output. Because we have W. That's what decides our output. Now, when we are training the network, what we are learning is the value of these weights. Because that's what we apply. Now, how do we know how good or bad our network is in the beginning or at any stage? What we do is we do a forward pass, like how we just said. Forward pass basically means you give an input, you see what the output is. Now, given this output, you need some way of quantifying how good or how bad it is, so that you can tell the network that this is how good or bad it is. Now, once we get that, we need to use that information and somehow change the weight so that the loss decreases. Loss basically means how bad it's doing, so you want to decrease the loss. The only way you can decrease the loss is if we change the W's, because W is what influences the output. But W is not directly showing up in this equation. Remember in this, we had the h4, it was a function of h4, then h3, then h2. So we need some way of getting the loss with respect to W. And because we can find this very easily, because it's right, it depends directly on this. It's like we have L equal to h4, W is C. And you have h4, which is W1, h3 plus D. What we do, if you want to find del L by del, it's actually just take a long little number. Math example. Let's say we have loss as the function of y, and y is a function of x. If I want to find the loss, the derivative with respect to x. Now, I don't have like expression of loss in terms of x, I have it in terms of y. So what I can do here, if you run chain rule, is you find it with respect to y, and then you differentiate y with respect to x. This is the same thing. So this would be the equivalent of, let's say, you know, y is equal to x. So if I pass it into this, you get L is equal to x4, and then L equal to x is 4x3. So to find this expression, instead of substituting this inside, here because we only have two variables, you can't directly put it. But now imagine if you have h4, you have h3, you have h2. Now first you put this in this, then this to this, then this to that, and then you calculate the derivative. That's too much. Simply what you can do is you can evaluate, you can use chain rule to get the final. L directly depends on y, so we differentiate that. Y directly depends on x, so we differentiate it. That's what we're doing here. Is we want to find it with respect to h1, but we don't have an expression of L in terms of h1 directly. So we'll use this in terms of h4, and then we just keep on. So anything gap means that's our guess. Y4 is an actual, L means loss. So, the more mathy way of writing this is loss at any with respect to the differential derivative of the loss with respect to any linear state at time step t is again it's just a math notation way of writing what we got in the previous slide. This method is called backpropagation through time because we're looking at through different time steps. We're going to understand like this basically. Just trying to see how each weight affects the loss and we try to minimize the loss. So that's why we modify the weights. So we'll do a quick recap. When we started off, what was special about language that required RNNs? We saw that there were some issues with the neural network. What were those issues? What is the main issue that required something like an RNN? Because models exactly. So in text, the history matters. So text is not just a bag of words. The meaning depends on the order of the words in the given sentence. So our model, if you take it just a neural net, it treats each word individually. It treats them as independent entities. But if you use an RNN, what it does, using that hidden state, it transfers the information that it gained from one word onto the next, and we can keep updating sort of a mental scratch pad into our while we wait for the seconds. In this, you have to see that word, it's not a bag of words, text is a sequence. Sequence is the main word here. The sequence is basically a list of things in which the order matters. Anything you can think of in which the order of the elements matter is a sequence. So if you look at frames in a video, obviously that matters because you're changing things in video focus. If you look at the stock price, let's say if I tell you over 3 days the price was 10, 100,000. That's telling you one story. If I change it to 1,000, 110, that's telling you a whole other story. So in that, also order matters. So stock price is also a sequence. You have sound waves, which are also a sequence because you can sound waves and the speech changes. So a sequence is just a list of things, but one extra rule, the order matters. So in a sequence, the future depends on the past. Now we established that if we change the order, the meaning changes. The future depends on the past. Sequence modeling is basically learning how the future depends on the past. So RNN, what we just did with text, is an example of sequence modeling because you are given a sequence and you want to guess what the next word will be. We're trying to learn how the particular words influence the next word. Now, a bit like a Mary will say this is, let's say you have a sequence, it's structured like this. This is your first word and this is capital T, which is how many words you have totally. What this equation says is the probability of the sequence occurring is the probability of the first word I'll write that for like let's say 3 words. So x1, 1, 3 would be x1, x2, x3. This is our sequence. Sequence meaning one word equals the other. Now what is this saying is the probability of this sequence occurring is equal to P of x1 into P of x2 given x1 and then P of x3 given. So how this captures the fact that this is a sequence is this is not just P or X2, we're also looking at the conditional probability. So we're saying given X1, what is the probability of getting X2? And then given X1 and X2, what is the probability of getting X3? So that's what makes this a sequence, that it depends on the previous inputs also. The last part is just, that's what we're trying to find, is that what is the probability of the output given this input. Again, it's the same thing if you just expand it. So that's sequence modeling. So RNNs also have their limitations. I'll just take a quick break and anyone has any questions. So if you remember the backpropagation, okay, backprop is a little tough at first, so it's fine if we didn't get it completely. But if you remember, we had this equation. Now basically what we do here is we do something like gradient descent, where let's say you're given some value W. You want to obtain that value. So what you do there is, this is your original and this is your new W. How you obtain this is you subtract the derivative of the loss with respect to W. This is called gradient descent. You guys want to get this? What gradient descent is you want to find the W that minimizes the loss, because obviously loss is bad. So we want to find some W that minimizes the loss. Let's say if these are all the ways that you get this loss, and this is what it looks like. This W is your ideal W, because if you see the loss is lowest when you get this W. So we want some way of finding this W, because in AI the functions are usually very complex. So we can't just do your direct method of saying real by equal to 0 and see what W you get. We can't do that. So what we do is we do gradient descent instead. Gradient descent is an algorithm of finding this same equation. That's what we do. Now this is how we update the base. This is our update rate. Now this is the gradient. But because the gradient itself is a product of so many numbers, if let's say a lot of numbers are less than 1. Right? So what happens here is, it's like, this is your gradient, this is the path that we're looking at. And if this is a product of a lot of smaller numbers, like let's say you have 10 pointers, you know what happens when you take a number less than 1 exponential? It becomes 0. So that's why the gradient vanishes. So what this means is, this term becomes 0. So net you are not really updating anything, because the change you are making is very small. So if the norm of this is less than 1, then it's called vanishing gradients because it becomes 0. What happens here is long-term dependencies are not there. What that means is it's not able to learn from the previous words. Why? Because this is, think of it as, let's say, 0.5 to the power something. If I have, let's say, 5 words, and I'm looking at the loss with respect to the third one, then I'll get 0.5 to the power 3 because I have 3 words in here. If I look at it with respect to the first word, then I'll get 0.5 to the power 5. So that becomes even smaller. The overall gain becomes smaller. So I'm not able to learn as much for this word itself. So I get short-term memory, which basically means I'm giving more importance to this. Again, that same context window issue. So that's the case of vanishing gradients. There's also another thing possible, and let's say instead of 0.5, it's like 100. And if you take this to the power 50, this explodes. It's very good. So that's the case of exploding gradients. Here, this whole thing just becomes very unstable because all your gates will become either very big or very small. So this is the first and sort of the main issue of RNNs. There's also another issue, and that's short-term memory. What this basically means is the RNN, implicitly, even though it has some memory, it's like once it reaches David France, by the time it reaches P, there is some area that it gives to France, some area that it gives to P. But as you see, it's decreasing every time you go forward. So by the time you reach speed, the amount of area given to France is not as much. But ideally, we don't want that because, like, let's say a word like I, that's a word like in, that's kind of useless. Like, we should obviously give France more importance than I and then in. So what an RNN naively does is it gives the latest word the most space in it. It gives all the words space in it. but how much each word gets depends on the location. So that gives a short-term memory, because if I have more words ahead, you'll see that the space that France has, it will keep becoming smaller and smaller, so it will not be able to access that. Should I repeat that? It was clear? So that's the second issue. And third issue is a bit more computational, is there is no parallelization. If you see in RNNs, we have to take in every single word. If I ask you to guess the fifth word, you have to read the first, second, third sequentially. We are not doing anything in parallel. And you must have heard of NVIDIA. And why is NVIDIA so big? Is because they sell GPUs. Now the advantage of GPUs is they can do calculations in parallel. Parallel basically means it can do 5 different calculations at once. But an RNN only does it sequentially, does one step at a time. So that makes it very slow. So training and inference becomes very slow. So that's my part. Give like a summary of what I've done. We started off with we want to look at how autocomplete works. So we looked at how computers understand words. We saw vectors and then not vectors. We also saw dense vectors, but that's not something we look at right now. And actually we will look into that. We looked at neural network for autocomplete. We saw what is a neural network, and then the issue with neural network. It has fixed input time. There's no memory, and also the order we should take that into consideration. Then we built an RNN by seeing how we humans read text and how we understand it. Once we finished the RNN, we saw that text is a sequence of anything in which the order of the things matters. We looked at other common sequences like stock price, video, things like that. And then we saw that unfortunately RNNs also have their drawbacks, short-term memory, managed ingredients, and you cannot parallelize now. So
what is the solution for that?
For
The drawbacks. What do you argue?
So there are different architectures. There is something called LSTM, there's something called GRU. It's not part of state space models as such, so we will not cover that. But if you want, I can send you like a link. Basically what it does is, RNN only has one line of memory. That's what we're trying to remember here. What LSTMs do is they have one line for long-term memory, one for short-term. So in long-term, it assigns only a few important words to that. So like France would get a lot of importance in long-term, but in short-term, maybe it gives you. That's a very simplified way of how it works, but that's like. There's also transformers, which is sort of that's the overall.
Okay, so Vedant talked about RNNs, and we use RNNs right now to do a little bit of translation. Let's say we have this sentence, Jaden is the best day, that's Jaden by the way, and we want to convert this to French. Jaden is a mayor leader, I don't know how to pronounce, sorry. So usually for these translation tasks, what we do is we have an encoded RNN and a decoded RNN. Your encoded RNN takes in your English sentence and it encodes it into, and it tries to understand the meaning of that sentence. So you have hidden state 0, 1, 2, 3, 4. It iterates over the sentence one by one. It encodes the meaning of the sentence, and then it sends this file, hidden state is sent to your decoder, which then tries to understand this meaning and output words one by one. So that is how we usually used to approach translation. But if you guys remember, Vedant talked about the fact that the information that is encoded from this state, this hidden state, may get very distilled over time by the time you reach this hidden state. So if I just go back to this slide of this, the word live, you can see that right now it has this much information. Now live is getting distant, and by the time we reach this state, you can see that the amount of information we encoded for the first word is no longer there, or it's very little there. So in tasks like translation, I would want Jaden to be my first output here, because logically in a sentence that I started with Jaden, I may require Jaden as the first output, but by the time we reach here, Jaden is probably one of the most irrelevant encoded aspects in an RNN, and we probably won't even have this as an output. So can anyone suggest some like fixes to this? What can we do such that this information, by the time it reaches here and it's sent here, we still, this block knows about all of this in a way that it knows about this. Yeah.
Start from that side and we are starting leader on that side essentially. So coming this time when we are writing something also we are reading from that side to that.
You're saying so after you output delete it?
After leader, we can lead related word and then start. We go to previous step and then that. That's only the elements of the word change.
Can you repeat it? What is the approach?
He's saying that you output leader and then you delete this and then
Start there and you're outputting in backwards.
backwards, okay.
So when you come to the starting words, the starting words will be in the words.
Right, no, but if you remember, we first encode everything. So by the time we reach lead, Jaden, the information about Jaden is already listed. So you're saying I send this and I delete this and then.
Or you're saying we should have maybe a bidirectional thing. You have one hidden state that goes this way and another hidden state that goes this way. That's interesting, and I think at one point that like this was an approach that people used to do.
But there is a paper on this, a slightly different version. They put the input sentence in the reverse order. So the input sentence will be eat this, is great, and then it will translate it in the correct order, and that actually improves the accuracy in those days.
Yeah, but that is not the preferred option anymore. But yeah, at one point they used to try things like bidirectional.
Yeah, they're called bidirectional.
Yeah.
Yeah, so yeah, that is a good solution. But
Anyone has any other?
yeah, any other?
While training you weigh the earlier ones more.
You weigh the other ones more.
Weigh the earlier states over the.
So I mean, it's
Now,
not.
how do you know that this hidden state has a lot of weightage? What if this is some irrelevant piece of work?
In general, you're still losing information about the earlier
Yeah.
right? So by giving it like hedging your memory is getting more.
Cool. Okay, so thinking around the same line, so what we do is we just give every connection away. What I do is I encode everything sequentially, alright? And then after I have some encoding, like here H1 has information about H1 and this one. This has information about the past and this and so on. What I do is after I have encoded everything, I connect each to every output. Okay? I connect each RNN hidden state to every output hidden state. Alright? And I have 25 connections. Now, what I do is I train my model in such a way that it learns to weight every connection. So now, probably Jaden, which is H0 and H0 dash, will have a very high weightage. And say leader and Jaden also have some correlation. So Jaden and leader will probably have some amount of high weightage as well. And like say the words don't really have any correlation. So maybe this and this don't really have that much of a weightage. So what we're doing is we're encoding sequentially, and then after we have encoded everything, we're taking these hidden state encoded informations, and together we're sending them over here, where we're saying that okay, this has this weightage, this has this weightage, this has this weightage. Each connection here has a different weight, corresponding to how we feel, corresponding to the logic of the translation. But not only this, like I'm encoding sequentially, and then after I'm taking my encoded sequences, I'm sending everything in parallel, and we will not feel that this is useless then, because I am taking my encoding and then I'm forgetting about the encoding and I'm just giving each of these connections away. So rather than going sequentially, why don't I just get rid of this? Why don't I just forget about this? Because each word is now connected to every output word, and each word knows how much importance it has to the output word. I don't really need to encode anything, because with these weights, I am telling the output RNN how much importance do you have to give to each word. And that really is the basic of something we call attention, and it is used in a very famous architecture we'll talk about. But essentially what we're doing is we're ditching the entire sequential encoding, and we just send everything in parallel. Now if you guys remember, RNN's main bottleneck was you have to go one by one, and your information gets distilled. So if we send everything in parallel, we are making NVIDIA happy, and we're also saving on so much time by sending everything together, and also we're doing it in such a way that now this information doesn't get distilled, this information doesn't get distilled, and this doesn't have a very absurdly high weightage. And that brings up the logic of attention. But before, obviously I can't just send English words into a model, and Vedant has already talked about encoding, but I'll just quickly brush up because we really need to understand this in depth to understand how attention works. Yeah, sorry. Yeah, so when you train a model, these are not fixed weights. We're not fixing these weights. When we train a model and we give it, so when we train a model, we have input and we have target. And after we train the model through backprop understands, okay, I should give this connection this much weight, this connection this much weight, this connection this much weight. And based on that, I mean, it's just training. The model figures it out.
You are right in the sense that you have to set up some mechanism such that the model is able to do this, right? So yeah, we'll get to that.
Yeah, we'll get to that. So this is just an intuition where, or my logic here is, okay, I know how this word is correlated to all these words. I know how each word is correlated to the other word. I don't need an input encoder RNN. I can send everything in parallel. How do we correlate them is something I will talk about with you. Any doubts?
What about the sequence? What if the same sequence of words could, in a different order, could mean something else?
Yeah, we'll talk about that. Yeah. Yes.
Doesn't this approach use context? You take the next word depends on the previous one.
Right.
Depends on the order, right?
Right.
So we are just ditching the order.
Yes, exactly. So we're currently ditching the order. We will talk about that in the future, and how even by ditching the order, we can still manage to get some work.
How do you know that we finally 5 words?
Yeah, so that is another issue.
5 words
Actually, yeah. So let's think about this. So right now we have, I think, 3 problems. How are we actually setting the weights to attend to each word? How do we deal with sentence length? And how do we deal with order range? Okay, and let us go sort it out in that order itself. Let's first figure out how we attend to different words. Then let's figure out how do we handle when as the sentence length keeps increasing, and then we'll figure out how to figure out the order. Okay, let's just answer those questions in that order.
Yeah, sure. Okay. So let's just quickly brush up on what Vedant talked about, how we make machines understand words. We use vectors, right? So obviously a machine cannot understand words. We cannot just give some random numbers. We use vectors because the way a vector points in one direction has some meaning, and we use that property of a vector to represent words. So as you can see, someone here has used some Star Wars dictionary and has encoded a vector space where you can see all the characters are closely together, all of the locations are closely together, and I think, I don't know, empires or time or something close together. And a simple example, a very common example is, if I encode the word man and woman in the vector space, and if I encode the word king and queen in the vector space, and I subtract them, the resultant difference vector will point in almost a similar direction. And another cool vector operation is if I, okay guys, can you tell me what will I get if I do king minus man plus woman? Or actually king minus man? I would guess something similar to queen. So that's how. So we use this really cool property where we have train machines to take words and represent them in a very high dimensional space. And this high dimensional space has somehow captured the meaning of words. So for example, if I have the word happy and joyous, they'll probably point in similar directions. And if I have the words happy and sad, they probably won't be very similar content. Like they may have some dimensions where they are nearby because they represent emotions, but at the same time they represent very different emotions. So in other dimensions they may not be very closely together. So you guys understand vectors, right? Vectors are basically we're taking the meaning of text, we're taking the nuances of a word, and we're representing them in a very high dimensional space. They can go above 3 dimensions. Some vectors.
Yes, make a guess for the size of the dimension.
Yeah, someone guess how many dimensions do we generally encode a vector? 30,000 is too much. Okay.
Yeah, okay, can you guess the vocabulary setting? Suppose you are working with English. How many words would be in here? 8,000 words. 8,000 words on the lower side, right?
8,000 words including the stuff you need to make other words up.
So he came up with a very interesting point. For example, playing is like play is a word. Ing is not really a word, but you can make up a lot of words if you just have ing as a special token, right? So yeah, but if you end up saving all possible forms of a word, you will end up going. But no, even that is not enough. 8,000 is on the lower side.
30,000.
Yeah, so GPT-3 came up with 50,000. GPT-4o uses 1 lakh.
This is vocabulary.
Yeah, Gemini uses like 2 lakh words. And but the dimension that they encode these 2 lakh words in is like 5,000. Like DeepSeek uses like around 5,000 dimensional vectors. Yeah, because it's fixed. So you're taking these 2 lakh words and compressing them into just 5,000 dimensions.
The parameter is relatively faster.
No, it's not. I mean, all of the LLMs are about the same size.
So yeah, you guys understand how we encode word vectors, right? Now that we know how we encode words, remember how I was talking about how I'm trying to correlate one word with the other word? How do I do that with a vector operation? Say I have one vector here and I have one vector here. How do I know how much this vector is correlated with this vector? How do I know how much one vector represents here? Yeah, dot product, right? So we use a simple operation called the dot product, and with that I can tell how one word is related to this word. So if I have 2 words in this dimension, in this orientation, I can tell how much of this word relates to this word, and that simple operation basically powers an entire attention mechanism. Okay, let's take 2 examples. The cat drank the milk because it was hungry. The cat drank the milk because it was sweet. What does it here correspond to? The cat. And what does it here correspond to? The milk. Right? And okay, for now assume there's some mechanism called the attention mechanism. And I've run the attention mechanism on these 2 sentences. And the attention mechanism, the darkness tells me how correlated the words are by dot product. So the attention mechanism ran on this sentence and told me it and cat have a very high dot product score. And on this sentence, the attention mechanism ran and it told me it and milk have a very high score. Do you guys not see something wrong here? Like, yeah, so I'm not changing how the vectors are correlated. So if I have the word it, I have V1 for it, vector 1. Say I have the word cat, that's V2. And I have the word milk, which is V3. I'm running dot products, I'm doing V1 dot V2, and I'm doing V1 dot V3. And in one case, I'm getting A is greater than B. And in the other case, I'm getting B is greater than A. We're still doing dot product, but how does that happen? We're not using RNNs, this is some parallel. Uh-huh.
So,
No. Okay, so let me just recap. All I've done is I've taken the words, I've converted them into the vector embeddings, and I'm just doing every possible dot product possible, and that's all I'm doing.
And you're doing some arbitrary operation.
Yeah, and I'm doing some operation called the attention mechanism. The attention mechanism just does dot product, but there is some slight modification we do, because look at this. In this sentence also we had milk and cat, but here the dot product is returning a high value for cat, and here when I have milk and cat, it's returning high dot product for milk. How does that happen? So essentially this let's call this the black box, where we have this attention mechanism. We're feeding in our sequence and it's outputting scores. Now this still runs on dot product with a small modification. And what that modification is, I'll talk about right now. So you guys know vectors in one direction represent one meaning, and if I rotate that vector in another direction, it represents some other meaning, right? And how do I rotate vectors? If I have a vector here, what operation do I do? What do I multiply it with such that I get some rotated vector? A rotation matrix, or just a simple, a matrix multiplication with the vector gives us a new rotated vector. So that's what we do is what the attention mechanism inherently does is it takes your input sequence, it passes it out. It takes your what I'm doing is quickly I'll just say my attention mechanism is somehow figuring out that it here refers to some living species and it here refers to some milk, because sweet is some flavor and flavor corresponds to food. So I am basically taking my original vector and I'm rotating them using matrices. I'll talk about this right now. But by the way, this is like this is the dimension size. So each row here is one word in a sentence. So the cat, blank, the milk, like that. Okay. We take this vector, we do that matrix multiplication, and we get 3 vectors. Okay. We call these vectors the query, key, and value. Now what I'm doing is I am taking my input vectors, I am pre-multiplying it with a rotation matrix called the query matrix, and I am now rotating my vectors in such a way that they pick up aspects, they pick up one set of nuance. So for example, let's say in this case I'm rotating in such a way that my vectors are picking up on taste. Alright, so I take my, forget about these two, I'm talking about this one. I take my input matrix, I rotate it in such a way that these vectors now correspond to taste. Alright, and now I take these are called my key vectors. I take this and I multiply it, and I'm saying I'm rotating my vectors again in such a way that they correspond to things that respond to taste. Alright, and what I'm doing here is, let's forget about the value matrix, forget about this. This is the main part of the operation. What I'm doing is, I'm taking my query, imagine this is like a log. I'm taking my query, I've rotated it in such a way that it's corresponding to taste, and my keys are the keys of the log. And I'm trying every combination, not by dot product. I'm saying, okay, this is talking about how this is talking about how something tastes, and this is talking about how an object is. Now, obviously, no one's going to taste a cat, and we're going to taste a milk. So we're going to taste the milk. So somehow these matrices have rotated my input sequence in such a way that when you're trying every combination out, it and the word it here and the word milk here will have a really high score. And similarly, if I rotate my vectors in such a way that my query is corresponding to some animal, then again when you're trying out all the dot product combinations, you're getting a dot product between these two such that it and cat have a really high score. You guys get that? That makes sense. All I'm doing is I'm rotating my vectors to capture some nuance of the text, and I'm running my dot product operations so that they match.
Which vectors are you rotating?
The input vectors. I'm taking my entire input, I'm taking all of them, putting them one by one in a line. I'm rotating all of the vectors and then I'm taking each combination and I'm doing plot line.
So your input matrix itself is being rotated.
Yes.
Wouldn't that, I mean, if your input matrix is being rotated, wouldn't that also cause changes in other
Meanings of other words. Yeah, so the idea is that you don't do all the rotations that you need right at the. So now again, this is like heuristic to tell that it rotates in terms of pace or whatever.
Yeah. This is.
But what we do is we rotate, but we don't rotate to like obviously then the claim is that the W matrices will need to know what to rotate to appropriately, which is kind of pain. So instead what you do is you layer these many times over. So in the first layer it does some rotations and it figures out that some words are correlated and changes the meanings around some way, and then you do some operations and then again you repeat this rotation correlation business, and then you do some transformations, again you do this rotation correlation, do transformations, and now you stack these layers one on top of the other, say 100 times. Then it's possible that somewhere in the middle, this repeated operation of rotation correlation transformation ends up changing, looking for taste. Okay. Then somewhere else it looks for emotions, somewhere else it looks for truthfulness, somewhere else it looks for harmfulness. So in that sense, you can like because you're trying to clear you'll answer. This is like the first part of the answer. I give you the second part of this answer at the end after the answer.
So in every round you take different matrices.
Yes.
Yeah, your matrices are different at every layer,
And are they random?
they're initially random, but they
They
are
get trained. They get trained.
Okay. Now
Wait, trained towards what? Because see, you said animal, taste, emotions, they're different things. So if you look at the vector space, they'll be in different parts of the vector space. So you should actually specify where all the vectors, so all the words live in some high dimensional vector space, all of them are getting mapped to one part of the vector space. I can say some subspace of the vector space.
yeah.
So how can you train them to go to different? So different emotions could be one vector, one subspace. Animals would be some other subspace. So how would it know if it's getting trained towards this? How would it know how to go to this?
Correct. And this is the thing about deep learning. We say that we train for it to go to all these subspaces, but this is actually an emergent property. What happens is we set up this entire architecture. We will show the architecture in a couple of slides, and you send in all the text in the internet, and you try to predict all text in the internet, and you look at then you peer inside the model, and like this thing suddenly works. Okay, it works very well, and you're like it doesn't make sense of how it works, and you
It's
go.
just working.
Yeah,
This
it's
is working.
working.
Yeah, it's like
And now what you do is,
Yeah.
okay, it's working. How does it work? And then now in the idea to try and figure out how it works, you peer into the model, and then you realize, oh shit, it's doing this transformation where it was meaning this thing, now it's meaning something else. And then now you have a post hoc explanation for it. So yeah, this is how usually deep learning works. You start off with a problem, like you had with RNNs. You come with a heuristic solution, and then you iterate, and a lot of people across the world are trying different solutions. Some work, some don't work. When one works, you're really surprised that it works so well, and people implement it everywhere. Then someone comes along and like, wait, it's working, but why is it working? And then you peer into it, and then you look into it, you realize, oh shit, right? Okay, the heuristic was kind of right. Even though at the start you might not be entirely sure of your heuristic, because you start with heuristics, then you optimize your heuristics by some random experiments, like not random in the sense that informed experiments, but they are not intuitive after a point. And then the model works, and now because the model is working, you can peer into it, and it starts making sense again. I will come back, I will explain this a bit more once I'm very
So are these weight vectors? So they are trained over some data, and they are now universal.
Yes.
Using them to train.
Yes.
They were training them, and now they have understood. Okay, I have to tend to this subspace and this
So
subspace.
can you just like download a query weight?
I mean, you can
Alright,
take an
yeah.
open source model and we can do it.
You see what it does?
In this case, the attention is some function that takes in that maps from the input word to the same
Yes.
In the previous slide,
Uh-huh.
you had input word to the same input word. What is input sentence? The
Yes.
these correlations.
Yes.
Like in the last example, it was from English to French.
Yes.
Over here, it's just English to.
Yes, so this is okay. The attention mechanism always goes this. It's first figuring out the relationships in that sentence, and then you give that to some output decoder which takes these relationships and then maps it to some translation patterns.
So even in that case, we first did an English to English mapping. All the words correlate with each other, and then we translated it into French.
And then you can correlate the French words to the English words and also do that.
Yeah.
We just took this example because it's easier to make a point, make this particular point here, right? The French example will become confusing. You have two operations.
Is the subspace of like taste defined?
Yes, as I said, while training this module, we don't define a subspace. We take the entire text from the internet and we make it predict the entire text from the internet, and then we tell it, okay, you're wrong here, you're wrong here, you're wrong here, and by telling it where it's wrong and where it's right, it automatically figures out.
So what we want our goal is to define where taste lies in our vector space.
No, we don't. So that's the thing about deep learning. You don't, as humans, we don't want to do all of these feature extractions because let's see, to model the world and you want to generate sequences, think about all the different concepts you'll have to extract, right? It's probably impossible for a human to sit and manually extract out all these concepts, assign them subspaces, and it's not going to work. So if you think about also, how many concepts do you think you need to model any sentence? You probably need millions of concepts. But you have only 5,000 dimensions. So even a subspace is like not optimal because subspace requires at least two bases, right? So something is off even there. The point here is that in the process of trying to make the best possible prediction for the next word, when you have a model that uses attention, it figures out how to use it in this way.
So what we are trying to do is we'll take a new word and we'll put it in the right aspect. Like it should be.
So we're not doing the
if it
model.
is sweet,
So,
I mean,
yeah.
if it is
so,
sweet, it should be in the taste subspace.
To clarify the point is, the subspace business is a post hoc explanation that we are giving. Okay, how the logic flow was, you have RNN, you gave parallel connection, you created this setup, it worked well, and then now you try to figure out how it worked well, and then when we are looking at it, you're like, okay, in this layer, all the stuff that relates to taste happens to be here, and the model seems to be rotating stuff to taste. Or for example, I was looking at one particular matrix, and it does a very interesting transform. It takes a country and it rotates the vector to the capital of that country. So if you take Afghanistan, it rotates into Kabul. If you take China, it rotates into Beijing. It does weird stuff like that. And this is a post hoc explanation I am giving you after the model has been trained. And I am just surprised that, oh shit, right, this is how it works. Yeah.
Good. Any other doubts?
You're rotating all the vectors and then taking dot product, right?
Yes.
If you rotate all the vectors, won't the
No. As I said, I am rotating this in one way and I am rotating this in another way.
But yeah, the same transforms apply to all vectors. Now, okay, Vedant will come back to this once again, but can everyone see? So you take your words and you convert it into vectors. You do this attention rotation business. Now this is your original vectors. Okay. Now you add your rotated business, rotated stuff to your original vectors. Now you do one, we call it attention. Now you do some operation. For now, think of this as a black box. I'm not going to tell you what that is. And you add that also. Okay. Now your next layer you're going to come back here, and again you're going to rotate, and again you're going to add, and again you're going to do some black box operation, and again you're going to add. So the advantage is your original vector is still there in this residual stream. Your rotated vectors are also there in the residual stream. So all aspects Like all the nuance you can capture because you're continuously adding to this memory bus.
Aren't you changing the vector? You're saying you're adding this vector to the original vector.
Yes.
So the original vector is lost.
Not lost. You're adding two vectors. So one vector magnitude is really big and the other one is very small. It's just like a delta change to the vector.
Okay, let's say that this one is big. So then
Yeah, if the vector here is very large in magnitude and adding a small vector, you can think of this as some connection to that vector.
but if you're adding something very small thing, it might not make a big difference, right?
Yeah, so it gets sorted out in how the model works, right? So again, we are not setting the parameters for any of this. This is you initialize all of these with random numbers, and then you do backpropagation and you train everything, and it works. But okay, fine, we can discuss more. There's some very good stuff that happens internally. We can discuss more after.
He's currently figuring out why it works. And yeah, so that's one of the clubs. It's called the data where we figure out why this works so well. So yeah. Anyways, yeah. So as I said, this rotation captures one nuance. How do I capture multiple nuances? I just do it one. And that's it. So that is the base of what we're doing. I will now dive into this. But can someone tell me? So by the way, we use this attention thing in a very famous architecture. Can someone name the architecture? Right? No. Okay. Gemini, Claude, ChatGPT, Grok, and so on. They're called LLMs. These LLMs work on some model. What is that model called? Can anyone guess? Yes, that's right. It's called transformers. And sadly today we will not go into transformers, but I will talk about this module of the transformer. It's called the multivector. And this is probably the most important part of the transformer, and this is like the heart of the transformer. And yeah, so I will ignore everything. We will take this block, we will zoom in, and we will slowly break it down. Cool? So a transformer has two parts. It has an encoder and a decoder. Remember, Jaden was saying we continuously encode. So that's what we do. We have this encoder block. Inside this encoder block, we have some attention mechanism. We run that a lot of times, such that in the end, when we reach this encoder block, it has picked up all of the nuances and all of the semantic meaning of every word in that sentence to the best of its possibility. So yeah, let's pick this encoder block and let's zoom in even more. Yes, that is your encoder block. And an encoder block has two big things: the attention mechanism, which we're going to talk about, and a feed forward. A feed forward is just a simple neural network. That's it. Layered norm, by the way, is just some mathematical operation you do to make sure your numbers just don't go crazy. And yeah, that's it. So this is an encoder block. Your vectors go to this attention thing. Attention outputs some vector which it thinks is the best possible encoded information, and then you pass it to the neural network, and then again you feed this into a new encoder block with different weights and different rotations, and yeah, that is it. So let's go into attention. Cool. So this is our input sequence. Say the sequence is the ball is blue. All I do is I have vectors for. Sorry. So I have vectors encoding the ball is blue. I just stack all of them together and create a matrix. Alright? That is my input matrix. Cool? The ball is blue, we do the encoding and we get the ball is blue. When we do encoding, we convert these into our input vectors, and some of you asked about how does it remember position, right? We do something called position encoding. I'll talk about it in the end because that's not what's concerning us today, but we do some sort of operation on those vectors such that they now know their relative positions with respect to each other. What exactly that operation is, I can talk in the end after everything's over, we can discuss it. Yeah. We take our input vector, we convert it to this encoding where now they're all vectors representing, these are words, the ball is blue, we convert them to vectors, the ball is blue. Each vector is an embedding plus it knows its relative position in some way. Now what I do is, I pass these vectors into query matrices, key matrices, and value matrices, which I talked about before, where we are again rotating them in some way, and we get the query vector for the key vector for the value vector for the ball is blue the same way the query vector for blue, sorry, ball, the is blue. Okay? Everyone's with me here? Cool. Okay, so now that I have my input sequence and I have query key value vectors, let's go. Okay, by the way, again, just iterating on the point, the way we convert these to these is via matrix multiplications, and these matrices have weights which are learnable weights during training if you learn. Okay?
Do all the words have the same Q, K, D matrices?
So yes, if I have an input sequence, they all get multiplied by one matrix and we all rotate them in. Cool? Yeah. Right. This is your the famous attention score. Let's just forget about everything. First, let's look at the heart. Let's look at this part. What is if I have a vector like this and a vector like this? What am I doing? This is Q and this is A transpose. What is this operation? That's dot product, right? So that's exactly what we're doing. We're doing the dot product. All right. We're dividing it by some value to just normalize it. Okay. And we're doing softmax. How many of you know what softmax is? Good. Softmax, for those of you who don't know, you have a bunch of numbers. You run this operation, e power zi by root of divided by sigma e power z, and you get probability. So higher the number, higher the probability. Lower the number, lower the probability. That's what softmax is. That's all. It takes in a number, it returns probability. Cool. So ignore this for now. What are we doing? We're doing dot product. We're dividing it by some fixed constant, and we're doing softmax so that each dot product result is some number between 0 and 1. Okay? And then we multiply with v, which I will talk about later. So let's just really just dumb it down. Q1, Q2, Q3, Q4, dot product, Q1, 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 Q2, Q1, Q3, Q1, Q4. We get this matrix with all of the dot products, and also assume that we've done softmax and root decay. So this matrix is, all these values are something between 0 and 1. And we also call this a factor matrix. The factor matrix is now containing information of each word's correlation with the other word, right? And can someone tell me what are the values of these diagonals? Yes, because each word is obviously correlated with that word.
They're not one.
Yeah, not one. Sorry, they're not one, but these will have the these will have the highest value.
At least at the start.
Yes,
at least at the start, they'll have the highest value.
Yes, because again, remember softmax does probability scores and.
So if what is the issue if we set it to 1, then all the others have to be 0.
Yeah.
Then the word can only attend to itself. That defeats the entire purpose.
Okay.
Yes, they're not one.
Cool. So dot product is done and we get this and then yeah. Okay. So if you guys remember, I said if you want to I'm so sorry, I didn't want to do it. If you guys take if you want to figure out how one word is correlated with the other words, we use a query for the query vector, and then we run dot product across all of these. And now this row tells me how the fourth word relates to the first word, how the fourth word relates to the second word, the fourth word relates to the third word, the fourth word relates to the fourth word. Good. Similarly, each row tells me how that word relates to the other words.
Wait, 1 minute.
Yes.
What does this mean again?
First word.
What does this mean?
First word.
Can the first word relate to the fourth word?
Not be symmetric.
No, but
It should not be symmetric.
it should not be symmetric. Ideally, it shouldn't even depend, because if the past depends on the future, like
No, it depends on what kind of language you're working with, right? Because there are certain languages which have different orders of.
It is like what the first word offers for the fourth word, and what the fourth word offers for the first word.
So,
they
like-
may not be related, right?
exactly. If you remember on Vedant's slide, you had something on this side. Probability of the xt plus 1 is a conditional probability over xt minus 1 x1, right? This is the setup we have. Now your claim is that PR of x1 is dependent on the future xt. This is sus because I don't know what I'm going to say 10 seconds into the future. So if I have to define a probability what I have to say right now, in the future, that's a little bit messed up, right? So can you come up with a solution for what to do that?
Only take the bottom half of the matrix.
Yeah,
Yes.
the lower triangle.
Take the lower triangle.
Okay. You guys understood what's going on, right? We found out the correlation. Now what I do is I take this and I multiply with the value vectors. Now, what are the value vectors? The value vectors are the same input vectors, and I have done some matrix operation with them, and I'm getting some set of vectors called the value vectors. Now, if you guys can see what we're doing, it's another simple matrix multiplication. We have a factor matrix, and then we do the value vectors, and then we get this output score. Okay, this output score. This operation is different, right? Why we do this as document method? So, yeah. Any doubts here? Fine. Okay. Now let's try to understand what exactly we did. Okay. Say I want to compute the score of Z4, which is I want to. Okay. Sorry. Before I go, this is what is happening is I have some. Say I given the fourth word to my attention module. All right. It's computing the score. It's outputting me some new vector which has information, which has information of how the fourth word is related to the first word. Good. Has some say x1 relation to the first word, has some x2 relation to the second word, x3 relation to the third word, and some x4 relation to the fourth word. That's all good. So yeah. So that's exactly what's happening here is Q4 or K1, these are all values between 0 and 1. And if I want to find the score of the fourth word, and I'm running the query across all of the keys, and I'm finding out how they correlated, and then I'm adding up, and then I'm multiplying it with that original word itself. So I'm saying, okay, this is the factor as to, this is the weight as to how much it's related to the first word, the weight of how much related to the second word, the weight of how much relates to the third word and the fourth word, right? So yeah, so we end up doing a weighted average, and the Z4 gets encoded with information as to how the fourth word has relations with the first word.
What are these? These are some weights.
No, these are not weights. So this is my dot product.
No, the V.
No, V is another vector. So here, I get V by another matrix.
You take your input, multiply it with another weight matrix, you get the V vector.
What does that signify?
So again, I told you about this. So I told you about a matrix that is rotating the country to its capital, right? The matrix that I was referring to was the V vector. So suppose the V matrix. Okay, I'm again throwing some sand in your eyes. It's V into another matrix, but okay, for now just bear with me and say that it's just the V matrix. So suppose you want to answer what is the capital of Afghanistan. Kabul is not there in that answer. How will you pull up Kabul as an answer? Whatever is there, it needs to take capital and needs to take Afghanistan, do some operation to get Kabul out. So V is this matrix that can do, we can do a lot of things because there are a lot of V's in this entire module. In one part, one operation that we could do is do these kind of transfers. Make sense? So if you have to get Kabul out, you take Afghanistan, rotate to Kabul, and then somewhere else in the future, you attend to Kabul and bring it to the correct answer. The capital of Afghanistan is, and then you realize the next one should be Kabul. So you know V has rotated Afghanistan to Kabul. So you take this Kabul and copy it there. Make sense?
So yeah, so now my fourth word has the weighted sum of the first two words, and yeah, that is the intention mechanism. Quickly, let's just recap. What we do is we take our words, we convert them to embeddings. Using the three matrices, we get the keys, queries, and values vectors. We do dot product of the keys and queries. So if I have 5 vectors in my keys and 5 vectors in my queries, it will be a 5 cross 5 matrix. And this matrix, the brightness tells the attention scores or values. And after that, we multiply with the values, with the value vectors to get our weighted sum. So yeah, it's kind of cool, right? A simple dot product tells you how correlated one word is with the other. and this kind of runs everything you know. So the next time you rant into ChatGPT, it's just a bunch of matrix numbers. And yeah, that's it. Now, can anyone tell me? So obviously, the good news is since each word is related to the other word by just dot products, we don't have an RNN issue of the meaning of the word being distilled, right? So, and also we don't have any Bayesian gradient because when we attend to some token here and some token here, it's the same dot product operation. We're not really using the H per se. And we can parallelize this because I'm sending all of my words in together. I can compute my matrix multiplications can happen in parallel. Yeah, so if you remember the RNN was says Jaden is the best leader. You have to follow that path. Jaden is the best leader. Here, if I want to find the relation between Jaden and leader, I can just do the dot product together. So the path is good. Compute cost. Can someone tell me what do I mean by compute cost? Like
how many cycles will it take?
Right. So if I'm tending every token to the other token, now we just took really short sentences, right? We just took a five-word sentence. If I have something which has more operations, n tokens, I have to compute an n cross n matrix which has O(n) squared complexity. So let's take an example. For example, you have a short text on WhatsApp. It has 512 tokens. That means we have an attention matrix of this size. And you can see how for a simple like a really long document, 32,000 tokens, we get a matrix size of 1 billion. And you can see how computing attention score. So, and not only that, if you guys remember, we are computing the attention score multiple times. So this is just us doing it once. We do it multiple times and multiple times in parallel. We have multiple heads, and each time we're doing it, we're having so many operations, and it really takes up a lot of compute cost.
Yeah, let's just put this into context again. We're saying we need 1 billion scores. Each of those is a floating point number. You need 4 bytes to represent one of them. So that's 4 GB RAM for just one matrix.
Yeah.
4 GB RAM for one matrix. And now you think about the fact that you probably need 16 of those matrices in one layer, and you need, say, 100 of that, so into 400. So that's like 4 into 4, like 1.6 TB of RAM just to work attention matrices. And we aren't even talking about the other parts of the transformer which you need. So you can clearly see how this very easily is going to get.
It shoots up. So yeah, just a simple demonstration of how every time DOS is just a token dependent transformer we starting, beginning of a sentence. And every time we add in a new word, you see how it is computing the lower diagonal. It has to compute the attention scores again and again and again and again. So iteratively as you go across and add more and more words, your computation cost just scales up. And yeah, that is the attention mechanism for you guys. Let's just quickly recap. Before that, any doubts?
You said you would not see the relation with the last word, but if you see the cat sentence, only the last word was changed. And based on that, you said it was related to cat or it was related to milk.
No, so that's encoding, right?
No, we'll come back to the sentence.
And you said why would previous words be affected by the later words?
Yeah.
So it is not looking at hungry or sweet, but it still changes its relation to cat or milk.
Yeah, so again, we hoodwinked you a bit. This is not the attention from the first layer. This is attention from some future layer, and it has done all kind of nonsense stuff like taking information from hungry and putting it in a word before this.
So we still look at the previous words are still related to the later words.
So previous words are
Only to the lower diagonal.
Okay, so again, no, it is not related to the later words. What also depends is which attention matrix I'm pulling this from. I can pull this from the attention matrix for the.
And just looking at the lower triangle.
Yeah, looking at the lower triangle.
At every attention cycle, only lower
Yeah.
triangle.
Yeah.
So the last word, no other word looks at the last word.
Yeah. Wait.
Last word is not being seen.
Good point. Good point.
I think this was taken from a bolt such that
Yeah.
the masking hasn't taken place.
See, even if it
In normal transformers, this won't be possible.
correct. So yeah, again we would you on multiple levels there. First, it's not from the first layer; it's from a later layer. Second, this is a model that was not trained on this causal regime. It was trained by masking. You remove this word and you try to predict the middle word based on the other word. So you randomly blank out 15% of all your words and try to predict. But because you're doing that, you don't do the masking. So in this model,
Yeah.
yes, what you're saying is right. In a causal model, it will work differently. Like for example, you take GPT, it will work differently. The attention patterns will look different. You're right, good point, good catch. This is taken from, I think this is taken from an article on Word, and Word is trained on this masked modeling type idea. Yeah. And also you had one more doubt about rotating all the vectors, right? Now, instead of thinking of it as just a rotation, we have a lower rank matrix, so it's a projection. Some of those vectors could be projected to 0, right? Like the null space in the matrix.
Okay.
So if that happens, then you can be selective about what you rotate and what you don't rotate. Right? So that's one way to get selection. And second thing, after this attention, you have this ReLU operation that comes in the next part of the transform, which we are not going to talk about today. But there, you're going to zero out anything that's negative and keep anything that's positive. It's like max or exponential, right? So then again, you have another layer of selection. So based on these two operations, you can sort out
So
the.
you only rotate some of the vectors and check how they are.
Yes, because the others you can, because it's lower rank, the others may get projected to none. That's again fine, but we can have better discussions on it. Right? This is just to give you a feel for our like introduce you to attention. We can discuss.
But at least this won't be picked up by the attention.
So
Please change.
I can pull up the like after the session. I can pull up the attention matrices for a causal model, and we can look at.
What is the cost?
So causal model is one where you don't let future tokens affect the past.
We will load it.
Yeah, we take the lower diagram. I can pull up a model that follows a causal language modeling idea, and we can look at the attention matrices there and see what's happening. Right? Yeah, you are right about this one being this was from Bert, and Bert was. Yeah.
Yeah, so we convert a word to embeddings, we send them to an encoder, the encoder has attention converts to query key value, and query and key are the dot product we do. And yeah, this is the formula. The dot product normalize softmax and then the weight sum is this. And yes, that is the attention thing. This is the whole overview of how we do attention. And the catch of this is the root cause, which we didn't talk about. And yes, that is any else? I think ours can go. Do you guys have a break? It was all good.
So we did a lot of AI, and it's very complicated, and you guys don't understand. So let's just do something simple for it. So I think all of you know answers that it's like everyone understands answers. So we just start with basic. So on the board as well. Yes, or I goes from there. So simple equation is EC, ES minus IR minus PC equals 0. This is the equation of the RC circuit, and the charge across the capacitor, you write it as Q equals C times Vc, and if you take a time derivative, you get dq by dt. With C dVc by d. This is very basic J stuff. I think everyone knows this. And the differential equation that we get from this, you can rewrite it as like this: Vs equals dVc plus RC RC is multiplied, RC plus we get this equation, and here what we're doing is we're treating the source voltage as an input, and the current voltage will measure. So like whatever we learned in the past class, you can think of this the capacitor voltage as the hidden state and the source as the input voltage. We're going to see how that's important to us in a second. So same equation we get as the hidden state is the input minus some derivative of it, some times of constant.
I mean, the electrical people, have you come across something called state variables? Have you come across state variables? So what's the state variable for that RC circuit, for an RC circuit? It's the voltage across the capacitor, right?
Yeah.
And like we have an inductor as current across the capacitor. So in some sense, you are modeling the change in the state of the system, right? So let's continue.
Right. So the same thing that we wrote, this equation, you can write it as a block diagram. This is a diagram that says that I give an input Vs, there is some plus operation happening here, there is an addition operation happening here, and I get an output Vc. Now the Vc goes back, gets a time derivative, gets multiplied by minus Rc, and gets added. So let's see how this works. So we give Vs, and what we're getting is Vc. Now from Vc, this is going back, getting a time derivative and getting multiplied by minus Rc and getting added to Vs. So time derivative of Vc multiplied by minus Rc gives us Vc of t. So this is the same equation that we had. You can represent this as a block diagram, and this is going to be important later. We're going to see how. But yeah. So we're going to take a small detour, and I think this is also very basic J stuff. How you define derivative in like the first order sense. So there's a curve, you take a slope, and you take a very small interval in which you measure like of h. So the derivative would be dy of dt would be f of t plus h minus f of t by h. This is called the forward Euler discretization. Basically, the first derivative is not very complicated. So this is basically you take the forward value. There is a backward Euler also where you take the backward value, and there is also a middle Euler where you take forward and backward. But for our case, we only need the forward value, and we're going to see how it can help us. Right. Now, suppose we are given a differential equation which shows something like dy by dt is f of t and y. So f of t and y is just the equation of the derivative, and dy by dt is the y is the output. So what we do here is we write dy by dt in this form as a Euler discretized derivative. We basically move from continuous time to discrete time. So we have this derivative, which is rewrite it like this, and I'll just show it on the board. So we rewrite it as y of t plus h minus y of t divided by h. This is there. You do a cross multiplication, multiply h here, and you move y of t. So what this essentially is doing, like the intuition behind this, is that you have y of t here at some point on the slope. Now you have this discrete slope, and this is multiplied by a small h, and you add it. So what this basically means is just moving in the direction of slope. So So instead of you being on a continuous curve, instead of you being on like this continuous curve, you're going like this. You're taking small steps. Like, these steps are really small, but you're moving in discrete times. You're not in a continuous curve. So this is what discretization is. Now, we just so this is instead of t plus h, I can just write k plus 1. So I can treat them as elements of the sequence. So y of k plus 1 is y of k plus h times f of t of k and y. So the derivative that we take depends on the previous time step, not on the forward time step. So because we are adding it to y of k, the derivative will depend on the previous time step, t of k and y of k. Now let's just go back to the differential equation, the RC circuit equation that we had. Right. Now here what we do some manipulation, simple manipulation. This time derivative of the voltage across the capacitor, we'll write it in the discrete form. So Vc of t plus h minus Vc of t by h. Simply we take we multiply to the other side and this 15 goes to the back. Right. So Rc v of t plus h, this is this figure. You take it to the other side. This is just manipulating the algebra. It's pretty simple. And so you get Vc of t plus 1 into this. And this is the discrete form of the same equation. So what you basically did was, you instead of writing it as a continuous time derivative, you wrote it as a discrete time derivative. You did some manipulation, you basically just did some algebra there. And what we got is the current across the capacitor can be written as a linear combination of the input and the current at the the voltage. The voltage across the capacitor can be written as a linear combination of the input and the voltage at the previous time. That is really important to us because as you can see, it's recursing input. So the voltage at the next step would depend on the previous step, and so on. This would depend on the step before that, this would depend on the step before that. So this gives like the exponential kind of equation which you know from the solution of the differential equation from the J. So we have this. Now let's just rewrite it again. So I didn't do anything, I just rearranged the terms. I took Vs common here and Vc K common here. And now I just treat h alpha equals to h by rc. So this is some constant value. H is a really small number, rc is a constant value specified in a circuit. So h by rc is equal to alpha, I can take it to be any constant. And so the same equation, we'll rewrite it. So Vc of k plus 1 is 1 minus alpha, Vc of k. So this depends on the previous value of the current across the voltage across the capacitor plus alpha, which is the input voltage. Now we can generalize this. So this is like in an electrical sense. You can do a very general version of this. So this Vc of x k plus 1 becomes x of k plus 1. This 1 minus alpha, let's just call it a, doesn't matter, any constant would go there. Because this is a constant, this is a constant, we can just call it a. And Vc of k, let's just call it x of k. Alpha we'll call it v. And Vs we'll call it u of k. Now here in this notation, what we are doing is x of k is the hidden state and u of k is the input. So Vs doesn't change, Vs goes to u of k, which is the input value. And x of k is the hidden state which is recursing in the relation that we have.
Wait, just to ensure that everyone gets it. Do you remember what the RNN equation was? What the RNN equation was? Vedant started with something.
Like the hidden state
You had
RNN equation.
some ht plus 1 is equal to
Activation of ht times
some activation, yes.
ht times the input plus some other.
So you're taking ht, doing some transform, whh ht,
then from the input.
whh xt and a bias. Okay. So what is the difference between between that and this, you just have
Yeah.
no arguments. Okay? That is where we are going, where we are coming from.
That is like the loop back. So it's similar to, very similar to an RNN equation, except that it doesn't have an activation. So now we'll dive into a little more math, which might be usually worse. So what I do now is, I take this equation, I take my RC circuit, let's just think of it in terms of RC circuit, and I put the initial value across the capacitor, or my hidden state is 0. And what I do next is, I said that my input is a Dirac delta. Now, what a Dirac delta function is basically a pulse. So I'll draw the functional form of Dirac delta. It's like this. So A is 1, A is 0, 0. So what you're doing in a Dirac delta function is basically giving the input and removing it. So you give it for like infinitesimal time and you remove it. So it is the impulse response of the system. The electrical engineering is coming down. So you give it this input and you see what the system is going to do after. You don't do anything, you just give it for the first second. This is the functional form of Dirac delta. If A is 0, it goes 1, and everywhere else is 0. So that is why we put the initial input as a Dirac delta function. We're going to see why it's important. This response that we get is called the impulse response. So when you give these values to this equation that you have, so let's just solve it. So x of, we put A equals to 0. So x of 1 is A times x of 0 plus B times U of 0. U of 0 is equal to delta of 0. And we just showed that delta of 0 is 1 if A equals to 0. So this becomes B. And because of our initial condition, x of 0 is 0, so this goes to 0. So x of 1 is B. Right. Everyone got this? Are there any doubts? If there is anything, so now this is x of 1. I'll just give this x a special name, h, because we're giving the Dirac delta. It's called the impulse response. We'll see why it's important and why. After this, I'll just move it to the next one. So h of 2 is A times h of 1 plus B times U of 1. Now U of 1 is 1 because everywhere else except 0, this is 0. So it's equal to 0. H of 1 we got from here, which is B. So we get AB. Now we do it similarly for h of t, which gives us A square B, and by induction, h of n would be A of n minus 1. This is the impulse response of the system. Okay. Now let's just try to substitute and back substitute in the equation that we had and see what's happening. So you had xk plus 1 as axk plus buk. Now xk you would write as axk minus 1 plus buk minus 1. So this xk, I'll just put it in and let's just expand it. So a times this. When you write it in expanded form, it will be something like this. Xk plus 1 a square x of k minus 1 plus ab of k minus 1 plus bu of k. So you'll see that in x of k plus 1, both the input at time step k minus 1 and k is coming, and the hidden state at k minus 1. So now we'll go further to see like if there is a pattern in this situation that will solve. There might be something. So you have xk minus 1, I'll put xk minus 1 again. So xk minus 1 would be axk minus 2 plus buk minus 2. I'll put this here. I'll solve it again. This I put here. Let's just see the solved form. So check this out. So you have a cube x of k minus 2. A square b u of k minus 2, ab u of k minus 1 plus b u of k. So here you notice that in the expansion of k plus 1, both like all three, k minus 2, k minus 1 and k is 1. So you would think that by induction, all the values of the input at all times are necessary for us, right? So when you basically keep going, k minus 2 will substitute, k minus 3 will substitute, you keep substituting again and again. You basically get a relation like this, which is basically x of k plus 1 is a of k plus 1 because a keeps getting multiplied and 2 is there, so it's k plus 1. I think it's clear. Do you guys understand how is it?
Everyone follow? Or is anyone lost?
Do you guys understand how we came from here to there?
Yes?
So, yeah, you keep multiplying a k plus 1.
Basically, like you saw that this was a recurrent relation, right? You had k plus 1, xk plus 1 depending on xk. You removed the recursion completely and you wrote it purely in terms of the inputs, not in terms of the state of the system. So you're finding what is the state at time t, given I have all the inputs that I've ever provided to the system.
So this goes to 0 because we had an initial condition that the capacitor is initially charged. There is no voltage across it. And here you can see that you can take B common out of it. And if you notice the pattern, whatever the coefficient of this is, it is k minus 1. So when it is u of k, this is k minus k, which is 0. Where the coefficient is k minus 1, it is k minus 1, which is 1. K minus 2, k minus 2, which is a square. So you can write it as a summation like this. K goes from n equals to 0 to k, u of k minus n u of n. I think if there's any doubt, let me know, I'll just explain it more. So, yeah. Now let's just come back to what we did, which was this. We got this impulse response, which is h of n is k of n minus 1 dt. Now, like what I'm saying is that you can write this output, what you had, in terms of a summation between the impulse response and the input. Like, this is my case, and we're going to see if this is true or not. So, what you basically do is you lift the impulse response. I don't know if this is intuitive to you guys, but you basically do a k minus 1, k minus n here, and you multiply it with the whole series of input that you have. So this is my claim that if I do a summation with this, I don't need to do a recursive relation. I can just do a summation at like one like it will take me like order of 1 time complexity to do it, because this is just like multiplying and adding, multiplying and adding. I don't have to do a recursive relation again and again. So yeah. Now if we substitute this value in the equation that we have, so this is my h of n, and I'll just write it like this. So x of k would be n equals 0 to k. Right, h of k minus n would be a of k minus n minus 1, right, times b into u of. So this is what I wrote. And this is what we have. This is what we had. Because it's k plus 1 here, you can subtract 1, k would come here, so the 1 doesn't matter. But what we got by a summation between the impulse response and the input is the same as what we got by doing the recursive relation again and again. So what does this tell you? It basically tells you that you don't need a recursive relation. You don't need to solve the whole recursion. You don't need to run a for loop again and again to basically compute the output sequence. You can do it with one summation if you just know what the impulse response is. And here you know by induction that you just need to multiply this constant factor again and again, and you can just get the impulse response. So this function that we just performed is called a convolution, what we just did. So x of k, you can write it as h of k, asterisk is a symbol for convolution, u of k. And you read it as the output is equal to the impulse response convolved with the input, and that will give you like the output with t basically. So this is intuition for convolution. So this might not be intuitive, it's a lot of math, but we're going to see how convolution actually works. So what we basically have is the impulse response is basically like a filter. So this comes here, this takes the value at every point, it sums it up, it gives the value here. So if you have some function which is like something like this, and you have an impulse response which is like this will basically move here. When this comes here, it will multiply these values, value of this and the value of this, the value of this, the value of this, this, and the summation of this would give you the convolved output at this point. So convolution is like a filter. You guys know about convolution neural networks. You guys might know. That also is like a filter. It works as a 2D convolution. This is a 1D convolution. It basically scans the input and sums it over the entire of the impulse response and gives the value. It goes to this time step, sums it all over here, gives the value. Third time step, sums it here, gives the value. This is what is happening in the convolution. This is one more. This is like a continuous time convolution. So this is your input signal. This is your impulse response. This is like your scanner. You flip it because it is minus. So I don't know if that's intuitive, but basically you flip it and then you move it over. And whatever the area under this curve is, will give you the compound term. Every time step, you get one value, and as it goes, it gives value for every time step. After a while, it just goes over. So that is convolution. If there is any doubt in this, please ask. Yeah.
Unrelated to this one, but
Yeah.
a plane had shown it, the equation.
Yeah.
Yeah. No, before. Yeah. So for this, you have not proved it, right? You have just verified it using the Dirac.
Yeah. So yeah, there is no. I didn't prove the thing. So I said that if I have this.
Correct. It's not give a proof per se, but now whatever you did for your first Dirac, you want to work it out for a sequence. Then you just think of your second Dirac as your first Dirac shifted by one time.
Yeah, you can keep shifting with it.
Think of a third Dirac as a first Dirac shifted by 2 times. Think of a sequence as a sequence of shifted Diracs. Repeat same argument. Works?
Got it? Any more doubts?
Siddhartha had asked very good question. Okay. We did all of this business. In RNN you have this activation function. Okay. HT plus 2 is equal to f of WHH. This is f of WHH HT plus WXH XT plus B plus WXH XT plus 1 plus B. Right? You cannot take it out of the function.
Exactly.
And that is the entire problem. That is what makes RNN sequential. RNN is sequential. That is like the issue, right? It's slow, it's not parallelizable, all of that because it is sequential. Because you cannot get this edge out.
But when you do not have the non-linearity,
Yes.
you lose the point of having a neural network.
Exactly. So now the point is, RNNs have a very nice property. It can model any function. I think if you go up, you can find proofs of how an infinitely wide neural network can model any smooth function. A sufficiently deep neural network with some width can model any function, all of that. RNNs also can model any function, but if you lose the nonlinearity, now that is a purely LTI transform. You can only do linear time invariant transforms, right? Yeah, good point. But we'll come back to it.
What is the solution for this?
What is the solution for this? We'll tell you tomorrow. So we have two issues. We want speed. Speed we got by getting rid of the nonlinearity.
Okay.
But we want expressibility also. So yeah, we'll tell you tomorrow. Any other questions? Do you guys see how the differential equation, like first order differential equation and the RNN, at least not the RNN equation, but the RC circuit equation? Can you give me one more thing? Okay, let's come back to, again to remind you guys, you know something like this, xt plus 1 is equal to a times xt plus b times u, right? Do you remember this? Whatever he did just now, are a function of time. The coefficients are a function of time. Can you do what he did? Yes, no?
We were here, right?
Next.
No, yeah.
Yeah. So this thing, now I'm saying these are functions of time. Good. Yeah, can you do this operation? Alright, but no, they are arbitrary functions.
Arbitrary functions.
Arbitrary functions. Okay. What happens is this won't be square, it will be a of t minus 1.
Like arbitrary matrices.
You still have to compute every single matrix. Little bit pain, right? One more pain point. Now this will work with numbers. Okay. Now suppose you have to do it as a matrix. You have to do how many matrix multiplications? You have to do n minus
Very
1
large.
matrix multiplications, which is also pain. Okay, so we need to figure out a way how to sort this out, right? We need to figure out a way how you can make this extend to vectors. If you extend to vectors, you need to figure out how to do these n matrix multiplications. That is one issue. That's computationally one issue. Second, you need to solve expressibility because this is a linear system. Yeah. And if you want to figure out how you can handle both of those, come tomorrow. Yeah. Tomorrow's will be a much more technical session where we go into putting up all of these basic ideas but putting them together to actually form what is a scale space model. Right?
Quickly
recap.
recap. So we started with words, like how do you represent words in numbers. Then we saw that words can be represented as like one-word vectors, like the whole vocabulary, 0, 0, 0, 1, 0, 0, like that. But there were a lot of issues with that because the vectors will be like very high dimensional, the vocabulary is very big, and it doesn't capture like similarities between words. So then we thought of word embeddings, like how we can do a discrete time, like continuous instead of a discrete word embedding. After that, we figured out what neurons are, neural networks are, and how basically neural network outputs probabilities instead of like word. It outputs like what's the most probable word after giving it a sequence. That was the basic of neural networks. Then we saw what RNNs are. We saw that because neural networks cannot capture the context in it. So we want to have the context in and we introduce the RNNs. And how RNNs tackle the issue of context by introducing a weighted state and script and all those things. And there were some issues with RNNs that it has sequential processing, so it is slow. And it also has a gradient issue, that the gradients grow up once you try to backpropagate it up. And the memory keeps fading up. So if the context, the important context is in the starting of the sentence, and you're trying to predict a word, at the very end, the memory of the context fades up. And that's kind of a big issue for us. And then we started a new mechanism called the attention mechanism. Then we saw how the dot product gives the similarity of words. How the attention mechanism basically does the whole sentence with the whole sentence, take a dot product, and basically captures which word is important to which one. So that was the attention mechanism, and I'm not going to dive into the math of that again. Like how queries, keys, values, all those things works in transformer, and that is the basic architecture behind all the modern LLMs that we use today. Yeah, the issue with the transformers was that it is very expensive to compute. The longer the sentence becomes, the bigger the attention matrices become, and it becomes very, very hard to compute, and it takes a lot of energy, it takes a lot of space, and it takes a lot of time. So what is the solution to that? The solution to that, we're going to discuss tomorrow, but before that, we need some mathematical basis, which is convolutions. So you saw that how a differential equation can be expressed as a convolution. You don't need to recursively calculate each value again and again. You can basically do it as a summation. So we saw that how like a differential equation, you discretize it and you basically do a convolution to get the output directly without doing all the steps again. So that is what a convolution is. And we saw the flip and slip involution. I hope you guys understood this one, how it works. This is the flip and scan method. And yeah, so binding everything together, this is only the first part of the Epoch series. Tomorrow we're going to see how we're going to tackle all the issues that we showed today, the time complexity, the sequential things, everything using a very new, very fresh architecture in the market which is called space-based models, and how it uses the mathematics behind the convolutions to solve time complexity issues, it basically brings it down from x squared to n log n and all those things. Tomorrow's session is going to be very technical and very interesting. It's like the new frontier in AI and all those things. So definitely attend. And yeah, that's it for today. I hope you guys
Also, if you
enjoyed the session.
want to figure out why we have a snake in our poster,
Yeah.
that also comes to mind. So, it's not because the session is in ESP, it's because.
Yeah, so that's all. Any feedback, any questions, anything? Yeah, sure.
Can you see the convolution?
This one, yeah.
So in convolution there is summation, right? At every instance are we just multiplying the values and going to third?
Yes. So what we do is,
Adding.
yeah, so this, you flip it. This becomes like a scanning signal. It comes here, you multiply the values of all the things. And this, at this time step it becomes. It's easy to understand in this.
Yeah.
So, it comes here, right? So you multiply all values. And that value becomes the value of the output at this time.
All lines take
The summation of all things.
all of them.
So this sum it all up becomes the value. When you move it one step, this, sum it all up, this becomes the value.
Okay. So from the point every future point.
Yeah, basically it's a scanner. So it's like a whole function. It scans, it comes here, you multiply all these values, you sum it up, it becomes the value. You move one more step, you multiply all these values, you sum it up, it becomes.
So like a specific part of the way.
Yeah, it's only this big, right?
Yeah.
Like that can be, in fact, that is fine. You keep summing, but you basically sum over the values, like you multiply and then you sum over. And it comes to these steps. And like how much step it moves gives the value here. Like which step it is.
Yeah, so basically now in continuous time, that sum will become an integral.
Yeah.
Right? So you are taking this, you flip the signal, and you shift the signal from minus infinity to plus infinity. As you shift, you take the overlap. So you multiply both, that's the overlap, right? So you are shifting, you can see minus t, the shift. And then you are moving tau goes from, tau is how you are parameterizing the equation now. So E goes from minus, yeah, fine. I am big.
Between
I got it. D tau. Correct. Yeah. Tau goes from minus infinity to infinity. So this function is getting, so minus t, so it's getting flipped, and tau is your shift. So it's going from minus infinity to infinity. Now when it's at a particular place, you are multiplying. So it's like this filter, right? So if you are multiplying here, you are taking only this section and you're integrating. So this section will be the area under the multiplied curve, and that area under the multiplied curve you are setting as a value at that point. So that is what this is doing. You have flipped the signal, you are shifting it from minus infinity to infinity. When it reaches a particular place, you are finding the area under the multiplied curve, and you are setting that area as the thing. So you see here, area is initially less, and at one point when it perfectly aligns the area, it's the top, and then again it starts decreasing, so it goes away. Make sense?
Yeah.
Okay. Yeah, that's all. If you guys have any doubts, you can ask. The session itself is over.